Hi, thanks for coming. I'm Pat LaChapelle, and today I will be presenting my research project, Seasonal Low-Wind Events in the Arctic and Associated Impact on Sea Ice Melt Parameterization in Climate Models. This project began in October 2019 under the supervision and mentorship of Dr. Madison Smith from the Applied Physics Lab. The Arctic Basin represents one of the world's most dynamic weather systems, and sea ice in particular has a substantial impact upon the global climate. This is partially because sea ice impacts a great number of variables, including salinity, temperature, ocean heat exchange, and more. Furthermore, many of these variables are intrinsically linked through various mechanisms, only some of which are understood and even fewer parameterized effectively. Currently, unmodeled and unparameterized processes pose one of the largest barriers to more accurate climate modeling. One well-established example of such an involved process regarding sea ice is the ice albedo feedback loop. This phenomenon is rather intuitive. Sea ice has a high index of refraction, reflecting most of the heat and energy from the sun back into the atmosphere. As ice melts, dark open water begins to appear in the system. For the same reason you probably avoid black shirts on hot summer days, the dark water absorbs most of the energy from the sun, subsequently raising ocean temperature and causing the ice to melt faster. Faster melting ice in turn means that there will be even more open water, thus more heat absorbed, and the cycle continues. As one might imagine, the effect of albedo can be exaggerated over certain sea ice characteristics, including what are known as leads. Looking to the right, we see an aerial view of an ice lead, defined by the National Snow and Ice Data Center as narrow linear cracks in the ice that form when ice flows diverge or shear as they move parallel to each other. Here's another aerial shot, this time showing an ice lead at the location of the Mosaic Arctic Expedition, which is currently ongoing and collecting data. I mentioned in the previous slide that leads happen when ice flows diverge or shear. In this lead, divergence is the culprit, which is apparent from matching characteristics on either side of the lead, circled here in red. We can see the opposite effect highlighted here in purple. These are pressure ridges, the result of converging ice flows. Such features are numerous in the highly dynamic environment of sea ice. In 2003, Dr. Marika Holland published results from a Shiba case study, finding a correlation between an extended period of low wind and increased stratification of temperature and salinity in leads. Holland measured lateral melt rates to be roughly 10 times the average. On the bottom right is a plot from Holland's paper in which the wind speed appears to be below 6 meters per second, denoted in red, for some time. Furthermore, up top, also from Holland's paper, is a figure differentiating the lateral melt rate from basal and surface rates. On the left is the same plot as last slide, though I've marked it up so that we can see more easily the start and end of the event, indicated by the blue lines. So you may be wondering, why does this happen? Stratification of salinity and temperature is the separation of layers, like we see in a bottle of Italian dressing. Shake the bottle of dressing and the stratification will disappear. The same thing happens when high winds drive turbulence in ice leads. A sustained period of low wind, circled in red, is the equivalent of setting the dressing on the counter. Fresh water from the melting ice is less dense and will therefore favor the top, as is demonstrated by the decreasing salinity at right. This water will then stay at the top, collecting heat as shown on the temperature plot and increasing the melt rate, a pattern we recognize from the albedo feedback loop. Finally, as high wind speeds and turbulence return, the fresh water at the top is mixed, and we see salinity and temperature return to base levels. While the dressing may only take 15 minutes to stratify, the lead water will take a fair amount longer to do so. This is why, for instance, we don't see the same phenomenon occur around day 215, even though the wind speed is below 6 meters per second. It must stay there for a sustained period. So here's an animation showing the effect of an extremely basic version of such an event. Since these are unaccounted for in climate models, the white is the actual retreating ice edge, and the pink shows the discrepancy between the observed and simulated ice. In short, the goal of this research is to make the pink area as small as possible. Primary analysis involved looking for obvious trends in Arctic wind. We use NCEP NCAR reanalysis data, looking at years from 2010 to 2019. Reanalysis combines modeling with actual data, working to fill in the gaps. This is essential for regions like the Arctic, where adverse weather conditions make reliable and regular data collection extremely difficult, sometimes even impossible. On the right is a simple plot of average wind magnitude during the summer over the last decade. Looking at this plot, we should remember that low average wind does not necessarily indicate a high frequency of events. Defining events is slightly more complicated. It requires clear, concise, and conservative criteria. Here's a flowchart outlining the logic used to extract the events from the wind data. This is based off of Holland's findings, though further analysis, experimentation, and observations may change the criteria in the future. We require a wind speed below 6 meters per second, sustained for at least 14 days. This must occur during the summer months, and of course, it must happen over ice. Once identifying and classifying events, we can look for trends in their location. This plot pretty clearly shows a tendency for events to occur near Greenland, as is indicated by the deep red colors in that area. Next, we determine how these events occur according to time. The blue dots here represent the percentage of total ice area at which events occur, averaged over the 10-year period of investigation. The teal line represents the moving average of the data points. Distribution appears to be relatively constant, though there is a high variance in the data, with most extreme outliers being found early on in the melt season. So we've looked at spatial and temporal distributions, but the phenomenon only occurs if the event is over an ice lead. To estimate the probability that the event occurs over a lead, we utilize sea ice concentration data. This is kind of intuitive. Less ice indicates more leads, though there are other characteristics, such as polynyas, that can also contribute to a lower concentration. We must keep this in mind. We examine ice concentrations over 30%, which is on the higher end of thresholds used, in hopes of finding further patterns. So here we compare the average ice concentration of sea ice in red to the average concentration of sea ice at events. Each line is plotted as a percentage of the respective total. The two lines appear to be very closely matched, and we see a discrepancy towards the right side. Taking a closer look at concentrations below 0.9, we see features in the red ice line mimicked by the event line in blue, which indicates a strong correlation in this range. At concentrations over 97%, the event line surpasses the ice line, showing that events occur over solid or close to solid ice with disproportionate frequency. Finally, we examine how the ice concentration at low wind events changes over the summer. This plot is averaged over the 10 years we examined. The red dots represent the average ice concentration of events occurring on that day, and the red line is the moving average of these data points. Excuse me, I had to take a sip of water. The blue line represents the average concentration of sea ice at that point in the summer. We see that the lowest average concentration of events occurs around mid-August, thus indicating that events might have a larger impact during this time. This concludes our findings, bringing us to final conclusions and future plans. At this point in our research, we have found a few trends. Events occur with higher frequency near Greenland. They are disproportionately likely to occur over highly concentrated or solid ice. Events could have highest impact in late summer. And some future ideas for this research include finding out how long events last, using other reanalysis data sets, using a wider range of years to reveal longer term trends, and of course the end goal, developing a model parameterization of these events. Finally, thank you to my mentor, Maddie, for all of her help. I've had a lot of fun on this project and learned a great deal. She's currently en route to the Arctic for the Mosaic expedition, which I mentioned earlier, and she'll presumably spend some time in actual leads, which I think is about the coolest thing you could get paid for. Thank you all for coming. I hope you've enjoyed this and perhaps you even learned something fun. Have a nice day.